So today we're starting length contraction. Here's the equation for it. Notice how it's different from time dilation. Time dilation means that relative time measuring an event is longer when measuring it from a different reference frame. Whereas in length, the relative length of something measured from a different reference frame is actually shorter. So the length contracts. That means L is less than L naught. So there's a contraction that happens. Now this is only observed from a relative frame of reference where you have motion and a velocity that is significant portion of the speed of light. So here's a question, very typical. If a 55-meter long spaceship, where that's measured at rest, passes Earth at 0.9 c, or 90% the speed of light, how long will the ship be as measured by a person on Earth? Pause the video now and see if you can calculate the value. Okay, so when we solve this problem, what we get is L naught is 55 meters, and we know that V is equal to 0.9 c. So when we plug these values in to the equation above, it's very straightforward. We just get 0.9 c all squared divided by c squared, and we end up with 55 times the square root of 1 minus, now the c squared here cancels with this c squared, so this c squared cancels this c squared, but then we have 0.9 squared left. And when we evaluate that, we get 23.97 meters, or roughly 24 meters length. So it goes from being 55 meters at rest to 24 meters as measured from someone in a relative reference frame. So here's another question. If an asteroid traveling at 0.8 c past Earth is measured to have a length of 5 kilometers, what is the length of the asteroid if it was measured by a person on the asteroid? In other words, from a reference frame of the asteroid itself. Pause the video and see if you can figure out the answer. Okay, so to solve this problem, notice that we're going to have to use the 5 kilometers. What is that? Who measures this 5 kilometers? So that's measured by a person on Earth. So if this is the asteroid and it's 5 kilometers, it's measured by a person who is looking at it from Earth. Therefore, that 5 kilometers is actually L. But what we're looking for is, what would a person standing on the asteroid measure it to be, right? And it's traveling, we know it's traveling at 0.8 c relative to the Earth. So that means we're looking for L naught, and we know V is equal to 0.8 c. So now we have to take this equation and we need to rearrange it such that we're solving for L naught. So now we would go L divided by 1 minus V squared divided by C squared is equal to L naught. And so now we could plug it in and we could say, all right, 5 kilometers divided by the square root of 1 minus 0.8 c squared divided by c squared. That gives us the c squareds cancel out, and we're left with 5 kilometers divided by the square root of 1 minus 0.8 squared. Don't forget this. Not only is the c squared, but the 0.8 is squared. So that would give us a value of 8.33 or 8.3 kilometers. So that 8.3 kilometers is measured by the person on the asteroid itself. That's the person that ends up measuring the 8.3. This person on Earth measured it as being 5 kilometers. Okay? Notice the length contraction happens for this person in the other reference frame. The length as measured at rest is longer for the person on the asteroid, because 8.3 is longer than 5. That's the end of this problem.